Final location, the airport. Often, especially in more complex proofs, several proof techniques are combined within a single proof. For example, within a contrapositive proof, we might need to show a subproof using contradiction or by using cases. This section does not introduce any new theory. We will merely be presenting two examples of such proofs within proofs. But first, a short clarification. You may have been wondering about the clear difference between contrapositive proofs and proofs by contradiction. So here in this note, I want to address this issue. And so we will assume that we have a theorem if P, then Q. If we were to prove that theorem using contrapositive proof, we would assume not Q and prove not P. This is simple and it never changes. If we were to prove that theorem using a proof by contradiction, then we would assume not Q and P, and then we would try to find a contradiction. So it looks a little weird because of the following reason. Oftentimes we assume not Q and P, and then we are led to prove not P. And we say, so we have not P, we have assumed P, and that's a contradiction. If that happens, really we didn't do anything else than a contrapositive proof. We assumed not Q, we reached not P, and we just say, oh, this contradicts P. If this is the case, you want to avoid a proof by contradiction. If you're doing a proof by contradiction and this is what you get, then you want to rewrite your proof as a contrapositive proof. It's more clear, it's more neat, and generally it's a more proper system of proofs. So if that is the case, our proof by contradiction is equivalent to a contrapositive proof, and we should write it as such for clarity. But there's another case that is not included in contrapositive proofs, and it explains why proof by contradiction is also valuable. It cannot always be rewritten as a contrapositive proof, and this is what happens. We assume not Q and P, and then we find another contradiction. So typically we can call it R. We find another statement R that was unrelated to the original theorem. It wasn't part of the original theorem, but we find R and we also find not R. So we have a contradiction that was not intrinsic to the original theorem, yet it's a contradiction and it completes our proof. Moreover, I want to add, and we'll see it in a few minutes, there are cases where we can use proof by contradiction when we don't have if P then Q, but we'll see that in a second. So, for our first example, we are going to prove the following proposition. Every non-zero rational number can be expressed as a product of two irrational numbers. That's kind of a surprise. It's kind of interesting. It seems a rather powerful proposition. The proof will actually exhibit an example of two irrational numbers that multiply to our rational number. So it's a proof that shows the solution. We will use direct proof. So we suppose that the rational number we were discussing is called R, and that means R equals A over B for some integers A and B. By multiplying the right side by 1, root 2 over root 2, we can write R equals root 2 times A over root 2 times B. Now this is what happens. Root 2 is an irrational number, and it's multiplied by what we hope is also an irrational number. And if that is the case, we have completed our proof, because irrational multiplied by irrational equals whatever rational we had. So, we know that root 2 is irrational. We only need to show that A over root 2 times B is irrational too. This is where our proof within the proof starts. For the sake of contradiction, let's assume a over root 2 times b is rational. This means a over root 2 times b equals c over d for some integers c and d. If we rearrange everything, we find root 2 equals ad over bc, and that's a rational number. But we know root 2 is irrational, so we have a contradiction. Consequently, r equals root 2 times a over root 2 times b is the product of two irrational numbers. It's as easy as that. Our second example is harder, even harder I should say, and it actually includes three different techniques that we've studied in previous sections. It's marginally harder than to prove that root 2 is irrational, although it follows some of the same ideas. So, suppose for the sake of contradiction that root 2 is rational. So there exist integers a and b such that root 3 equals a over b. Let's assume that this fraction is reduced, so a and b have no common factors. Let's play around with this expression in this exact same way as we did with root 2. So we take the square on both sides, and then we'll multiply by b squared, and we get 3b squared equals a squared. We'll come back to 3b squared equals a squared in a little bit. But before that, we start a proof within the proof. We want to show that if 3 divides a squared, then 3 divides a. We will use contrapositive proof to prove this conditional statement. Suppose 3 does not divide a. This implies that there is a remainder of 1 or 2 when a is divided by 3. So we have to split this into two cases. Case 1, the remainder is 1, and then we'll see case 2, the remainder is 2 in a little moment. So if the remainder is 1, then a can be written as 3m plus 1 for some integer m. Consequently, a squared equals 9m squared plus 6m plus 1, which can be written like this, and we see that 3 does not divide a squared. It's 3 times the number plus 1. So 3 does not divide a squared. The case 2 is exactly similar. We can write a as 3m plus 2, and when we calculate a squared, it's 9m squared plus 12m plus 4, and again, we have a remainder of 1 if we divide a squared by 3, so 3 does not divide a squared. In either cases, we have the fact that 3 does not divide a squared, and this ends the proof within the proof. We show that if 3 divides a squared, then 3 divides a. Just a short comment, we could have proven this fact separately before our theorem. We could have called it a lemma, and if we had done that, then our proof that root 3 is irrational would have just mentioned the lemma, saying, since we proved lemma number 25, we know that if 3 divides a squared, then 3 divides a. And it would have saved us this proof within the proof. Anyway, we did it here, and so now we're going to use the fact that if 3 divides a squared, then 3 divides a, by going back to 3b squared equals a squared. Here, this means that 3 divides a squared. Hence, it implies that 3 divides a. So a equals 3d for some integer d. And therefore, 3b squared equals a squared equals 3d squared equals 9d squared. If we divide by 3, we get b squared equals 3d squared, and we see what's happening now. We find that b squared is a multiple of 3. And this in turn means that 3 divides b. b is also a multiple of 3. Now that's a problem because we have assumed in the beginning that a and b did not have common factors, and now we're saying that they can both be divided by 3. So we reached a contradiction, and this completes our proof. Thanks for listening, and I hope it was interesting.